Chapter 7 is about magnetic fields and how magnetic fields affect moving charges in a magnetic field. And so the first thing we want to talk about is the field surrounding a magnet. So if we look at the pictures down here at the bottom, here we can see a magnet can be represented by a south and a north pole, or a south and a north pole, and we can determine the field surrounding this magnet by using a compass, and the compass will show the direction of the magnetic field and also how fast the needle of the compass changes will tell us something about the strength of the field. So that's one way to figure out the field lines for a magnet. So the direction of magnetic field B is out of the North Pole. We can see the arrows coming out here, and around and into the South Pole. So we can see here, a lot of times we'll use a magnet, and if we're looking for magnetic field lines, say, if I wanted to say magnetic field lines are to the left, I could imagine taking a magnet and putting it close to a moving particle, and the field lines here are pretty close to straight, and I can imagine these being my field lines to represent my magnetic field. The field lines, again, point from north to south, and the field lines form closed loops. That means I can't have a field line coming out over here and then go off into space. It's always going to come back around and come back into the South Pole. And the number of lines per area is proportional to the field strength. So you can tell my field strength here, close to the north end of the magnet, is much stronger than my field line, say, out here, where there aren't as many lines. So that is another indication of field strength. For magnets are similar to electric charges. So just like with electric charges, if I have a similar charges, they repel. Here, the north faces of the magnet repel each other. The south faces repel each other, but the north and the south are attractive, just as a positive and a negative charge are attracted to each other. And the other thing is there are no magnetic monopoles. So for electric charges, I can have a positive charge alone or a negative charge alone. But for a magnet, I can never have a south pole without a north pole or a north pole without a south pole. So even if I were to take this magnet and break it in half, I would create two pieces that would both be magnets, each with a south pole and a north pole. And again, if I were to continue to do that, again, I would not ever be able to create a south pole alone or a north pole alone. So there are some very similar properties of magnets and charges, but they aren't totally similar. Magnets are similar to electric dipoles, and so if I look at the field of, and this is my electric dipole, right, I can see it's very similar to the field due to my magnet. So this would be the electric field, and this example would be the magnetic field. The other thing that's interesting is just as a dipole experiences a torque in an electric field, if the dipole, the direction along the line connecting the charges, isn't aligned with the field, it experiences a torque to go into that position, so that its line connecting the charges is along the field line. The same thing is true of a magnet. My magnet experiences a torque that wants to turn the magnet so that it is aligned. The length of the magnet is aligned with the field lines. Ferromagnetic material is an iron or another material that can be made into a magnet. So you can take a piece of iron and put it in a strong magnetic field, and you can create a magnet. And so the individual domains become aligned with the external field. So you can see here before we have just a piece of iron that hasn't been magnetized, and you can see that the direction of each of these domains is random. But once it's put into a magnetic field, there's a preferential downward direction of the magnetic field in each of the domains. Magnets can lose magnetism by dropping them or heating them above their Curie temperature.